All right, last one, ladies and gentlemen. No preamble, no funny intro or any of that other stuff. Let's just jump right into it. Talking about control of respiration. So, how does your body regulate how fast or how slow you breathe, how deep or how shallow you breathe? So basically, is what we're going to be talking about. So, let's see. We've got our peripheral and alveolar capillaries. This is one way that we control respiration rate, and so these are going to maintain rates of equilibrium, and diffusion rates through a number of different ways. Number one is local changes by way of oxygen delivery and changes in the depth and rate of respiration, which is going to be controlled by the respiratory centers. And so these capillaries are going to be sort of like some of the sensors, the localized triggers as far as changing in oxygen and carbon dioxide output and stuff like that. So the local regulation is going to be respond to rising carbon dioxide levels. So your activity level is starting to increase. So you're generating more carbon dioxide. Smooth muscles in the arterioles and the capillaries are going to relax. That's going to increase blood flow. We have something called the ventilation to perfusion ratio, which is going to coordinate lung perfusion. And lung perfusion is blood flow to the alveoli. As the blood is coming from the pulmonary arteries into the bloods and it spreads out into those capillaries around the alveoli, that's known as lung perfusion. And so that's going to coordinate blood flow with blood flow to the alveoli with your airflow. Remember, we talked in the last video how those movements are coordinated to maximize the amount of oxygen and carbon dioxide we're exchanging. Changes in carbon dioxide levels are going to control either how much bronchoconstriction or dilation that is happening. The respiratory centers of the brain that I mentioned a couple slides ago, these are going to monitor oxygen demand by way of carbon dioxide levels, and that's going to increase your respiratory rate. Now, there's voluntary control and there's involuntary control. All right, so there's a number of different places that the rate of respiration is controlled. There are voluntary centers in the cerebral cortex, which is this area right in here. And these voluntary centers are going to control the respiratory center in the pons with these apneuristic and pneumotaxic centers, and the medulla oblongata, which is down here, which is some of the most basic respiratory control centers. And they're also going to control the motor neurons that are responsible for controlling the muscles responsible for respiration. The actual respiratory centers are pairs of nuclei in the medulla oblongata and the pons, which are part of the brainstem, right in here. They're going to regulate both the frequency of pulmonary ventilation and the depth of pulmonary ventilation in response to sensory information, stress response, elevated CO2 levels, stuff like that. Starting with the most basic, the rhythmicity centers are located in the medulla oblongata that establish the respiratory rate and rhythm, that sort of regular in-out motion. Each one of these is divided into two, the dorsal respiratory group and the ventral respiratory group. The dorsal respiratory group, as you can see over here on the left, is the inspiratory center, and it functions in both quiet and forced breathing. In quiet breathing during inhalation, the DRG is going to be activated briefly, which is going to stimulate those inhalation muscles. And then the neurons become inactivated to allow those muscles to relax. Now, the ventral respiratory group is active in both the inspiratory and the expiratory centers, and it functions only in the forced breathing. And so if there's an increased activity in the dorsal respiratory group, that is going to activate the ventral respiratory group. And we end up with the same thing. So the ventral respiratory group is going to stimulate those neurons that innervate those accessory muscles involved in deep breathing, and stimulate active exhalation in both the primary and the accessory muscles. The apneuristic and the pneumotaxic centers of the pons here at level 2 are paired nuclei. You can see right here. So there's a paired nuclei. They regulate the depth and the rate of respiration. The apneuristic center provides continuous stimulation to its own dorsal respiratory center. The pneumotaxic centers work to inhibit the apneuristic centers and promote passive and active exhalation. The interactions between the DRG and the VRG establish the basic rate and depth of respiration, and then the pneumotaxic centers modify that rate. So the baseline is set by those respiratory rhythmicity centers, and the pneumotaxic centers in the pons modify it, slow it down, speed it up, stuff like that. The condition that, well, it still is a big deal, but it surprised a lot of people 10, 15 years ago, was SIDS, also known as sudden infant death syndrome. And that is a disruption of this normal reflex pattern. Basically, the child would stop breathing suddenly and without warning. This could be caused by connection problems between the respiratory centers and the pacemaker complex of the brain. There are a number of different things that people can do to prevent this from happening, and a lot of the research as far as what goes in the bed of an infant and how they sleep and how they're swaddled and things like that has been because of research in relation to SIDS. So the respiratory centers respond to different bits of sensory information. There's chemoreceptors that measure partial pressures of carbon dioxide, pH, oxygen, as well as pH. Baroreceptors are going to be receptive to sinus pressure. Think of barometer as a device that measures atmospheric pressure. So baroreceptors are going to be sensitive to blood pressure. Stretch receptors are going to respond to changes in lung volume. Physical or chemical irritants are going to stimulate the nasal cavity, larynx, and bronchial tree. That's where we get coughing and sneezing. Then other changes include pain, body temperature, abnormal visceral sensations will stimulate the respiratory centers to adjust your respiratory rate. Let's see. Chemoreceptors receive a lot of input from a lot of the cranial nerves, including the glossopharyngeal, the vagus, and the chemoreceptors that monitor the cerebrospinal fluid. Chemoreceptor stimulation leads to increased depth of respiration, deep breathing, and rate of respiration, how fast you breathe. Chronic stimulation can lead to decreased sensitivity. This is a flow chart, basically a feedback loop of arterial CO2. Remember how fast and how deep you breathe is actually triggered by changes in the CO2 concentration, which corresponds with an inverse concentration of oxygen. So basically, if you have a state where there is too much carbon dioxide in the blood, that is hypercapnia right here. Chemoreceptors in the arteries and medulla oblongata are going to increase the stimulation of respiratory muscles, which is going to increase respiratory rate, decreasing arterial carbon dioxide partial pressure, bringing that down, also increasing oxygen. The opposite of that, too little arterial partial pressure, is hypocapnia, which this particular condition is hyperventilation. If you breathe too fast, too much oxygen is your blood. Basically, then the reverse happens and your breathing slows down. Now, hypercapnia is also known as hypoventilation. This one we don't use as much. You're not getting enough oxygen. So, like if you start some sort of strenuous activity where your heart rate increases, your metabolic activity is increasing, you're generating more carbon dioxide, you are hypoventilating. If you are bringing in too much oxygen, not enough carbon dioxide, you are hyperventilating, and so basically your body forces itself to slow down. Baroreceptors are going to be stimulated in the carotid and the aortic arteries, and so these are going to have an effect on blood pressure and respiratory centers. If the blood pressure begins to fall, respiratory rate is going to increase, and the inverse takes place when blood pressure increases, respiratory rate decreases. And the reason why this happens is increase in blood pressure is going to drive more oxygen more quickly to various tissues, so your respiratory rate is going to decrease because you're moving so much oxygen around, and then vice versa happens if your blood pressure falls. Within the breathing, the quiet breathing and the forced breathing and stuff like that, are the Hurrig-Brauer reflexes. These are two reflexes involved in forced breathing. We have the inflation reflex, which prevents overexpansion of the lungs. Basically, you can't burst your own lungs. And the deflation reflex, which is going to inhibit expiratory centers and stimulate the inspiratory centers during lung deflation. And so basically, you cannot collapse your own lungs either. The reflex is an uncontrolled action that your body is going to do in response to these different structures. Other protective reflexes are triggered by receptors in the epithelium of the respiratory tract when exposed to different things like toxic vapors, chemical irritants, mechanical stimulation. This leads to sneezing, coughing, laryngeal spasm. Your throat closes up, basically. If you're in the water, right, and water is coming into your mouth, you're actually experience a laryngeal spasm, so your throat, your airway will close off to prevent water from going into your lungs, because that could cause a lot of damage to those very delicate interior spaces of your lungs. A disruption of this regular breathing pattern is apnea. So sleep apnea is a very common condition that strikes a lot of people. That is a period of suspended respiration. Typically it happens, like sleep apnea happens while you're asleep, but basically long period of time where your breathing stops, basically. This is typically followed by a forceful expulsion of air to remove whatever the offending stimulus is. This would also, like regular apnea, especially if you are doing a forceful expulsion of air to remove the offending stimulus, you're choking. Food is lodged in your throat. You do abdominal thrust with a forceful expulsion of air to remove the offending stimulus, whatever the food particle is, because you were eating too fast and talking while you were eating. Involved also in sneezing and coughing. So basically your breathing pattern is paused while you're coughing or sneezing to get this stuff out of there. Laryngeal spasm I already talked about. I jumped the gun and I apologize. The airway is temporarily closed to prevent things from coming in that aren't supposed to come in. All right, voluntary control of respiration. You can voluntarily control how fast or how slow you're breathing. Strong emotions can stimulate the respiratory centers of the hypothalamus, which can activate sympathetic or parasympathetic divisions of the autonomic nervous system, which can lead to bronchodilation in the case of the parasympathetic division or bronchoconstriction in the case of sympathetic activation. So fear, relaxation, anxiety, for example, something that's kind of interesting, and we'll get into this a little bit later, is your body gets into an anxious state. You feel anxious, and part of that is because of oxygen levels in your blood. They get too low, your body becomes stressed. So deep breathing exercises help working on that. Also, anticipation of exercise can increase respiratory rate and cardiac output because your body is ramping up for the activity that's about to come. All right, ladies and gentlemen, we are in the home stretch in this one. We're going to talk about a few age-related changes in respiration. What happens to your breathing as you get older? So, before birth, your pulmonary vessels are collapsed because there's no air. So your lungs aren't functioning. The lungs don't contain air. During delivery, the connection between the baby and the placenta is lost. Blood oxygen falls, blood CO2 rises. At birth, the baby overcomes the surface tension in the lungs to inflate the bronchial tree and the alveoli and take the first breath. A lot of doctors will they want to hear that scream when the baby comes out, that cry, because that means the lungs are working. And what's kind of interesting, if the baby doesn't cry, in some cases they will induce the baby to cry. So like with my oldest son, they actually slapped the bottom of his foot to make sure that he would start crying, just to, really tick him off and stuff like that. Because they want, when they do that cry and they take that first real big breath, that's them making sure that the lungs are working to flush out all the rest of that stuff. A lot of that liquid that the baby was in gets forced out during birth as the baby is squeezed through the birth canal. There's also a large drop in pressure, which pulls blood into the pulmonary circuit. The foramen ovale and the ductus arteriosus, those were structures that are in place while the baby is in utero. Those structures actually close, and then the fetal blood circulation patterns redirect into the normal circulation patterns. Remember, the foramen ovale basically allows the heart to skip the pulmonary circuit, and so at birth, that bypass gets closed. Now, there are some cases where that bypass is not closed, in which case they, after they do diagnostic tests, they have to go in to do surgery to close that. Subsequent breaths as the baby is crying will fully inflate all the alveoli. So hearing that baby cry the first time that they're born makes a whole lot of people happy for a whole lot of different reasons. As you get older, the elastic tissue around and sort of embedded within a lot of the lobes and everything like that begins to deteriorate. That means compliance is going to decrease, making it more difficult to breathe, having to do more force, and lowering your overall vital capacity. Arthritic changes, typically as you get older, you're more likely to develop arthritis. That's going to lead to restrictions in your chest movement and limit respiratory minute volume. Emphysema, which is a decrease in lung function. Okay, a chronic condition of decreased lung volume is emphysema. Now, emphysema is you're at greater risk of developing as you get older, especially over 50. Basically, what happens is the air sacs within the alveoli bursts. So you're decreasing the surface area for that gas exchange, basically. The extent of the emphysema depends on your exposure to respiratory irritants. So if, for example, if you're a chronic smoker, your emphysema, you're going to develop it sooner, it's going to be worse. If you're in places with a lot of air pollutants or something like that, you're also at risk of developing emphysema because of those respiratory irritants. This is a chart showing a decline in respiratory performance starting at age 25, which when development is done, basically, and you don't have any development of the lungs and stuff like that. And as you can see, even if you've never smoked, your respiratory performance decreases over time because of that lowering of the compliance and stuff like that. Now, if you smoke, that's the solid red line there, it decreases a whole lot faster. Now, you'll never regain your lung function if you smoke. The only thing you can do is basically stop the rapid decline. So, for example, if you look at this, if you stopped at age 45, your lung function is still declining. It's just not going to decline as fast as it was if you had been smoking that whole time. Now, there is a certain level. If you're just above 25% lung performance compared to what you were at age 25, that's considered disability. And so you have to have oxygen supplementation pretty commonly at that point. If you continue smoking, if you are less than 10% or so of respiratory performance compared to what you were at age 25, that is death, basically. And so as you can also tell, your quality of life and your life expectancy also decreases. So right here, if you stop smoking at age 65, death will come more quickly than if you had never smoked due to the lung damage that was caused. Now, that's not a definite rule. There are some people that have smoked their entire lives up until the day they died, and they lived well into their 80s, and then there's other people who had never smoked, worked out, ate healthy, exercise and stuff like that, and they still die early, But generally speaking, and here's the soapbox thing again, Mr. Thompson's going to climb up on top of. Don't smoke. It shortens your life expectancy. It reduces your lung function. And nobody wants that. It's hard enough to get around and move and breathe when you're older. To begin with, don't make it harder for yourself. All right, stepping down off the soapbox now. Last couple of things we want to talk about is how the respiratory system is integrated with some of the other structures that we've been talking about. So the overall goal of respiratory activity is to maintain O2 and CO2 levels in the peripheral tissues. It doesn't get too high, doesn't get too low of either ones. And so this requires coordination between the respiratory and the cardiovascular system. So that connection is pretty right? That's why in this particular project, we're putting these two systems together. So specific ways that these two systems are integrated with each other. An integration of these two improves the efficiency of gas exchange by controlling lung perfusion, controlling the blood spreading to those capillary surfaces, increasing respiratory rate and blood pressure through chemoreceptor stimulation. Those chemoreceptors are monitoring CO2 levels in the blood, basically. Raising cardiac output and blood flow through baroreceptor stimulation, so monitoring blood pressure, which can be affected by the partial pressures of the gases also. Your respiratory system is the main way that you get oxygen for a lot of your other systems that you're looking in here. So the oxygen that your muscles need is going to come in from the respiratory system. All of the other systems, the nervous system, as far as the cells are working, they're generating carbon dioxide. That's going to travel through the blood, part of the circulatory system, to the lungs where it's expelled. There's the respiratory system. And so there's real tight integration between all of those systems. Basically, all the oxygen that all these other systems need to function comes from the respiratory system. Well, ladies and gentlemen, I know it's hard to believe, but we finally made it to the end. The respiratory system, good night. It's super duper complicated. So we're going to kind of spread these out a little bit because that was a lot just for the respiratory system, and we kind of split things up a little bit better than in the circulatory system. So go back and kind of take a little bit of time to look at those. Other videos, look at this videos, be able to sort of diagram what the partial pressures are at the alveolar sacs versus the pulmonary capillaries versus the systemic tissues and stuff like that. We're not going to do a whole bunch of stuff about calculating partial pressures. You just need to know how those partial pressures drive those concentration gradients. Here pretty soon, we're going to be getting, if we haven't done so already, we're going to be getting into our project, looking at the cardiovascular system by itself, looking at the respiratory system by itself. There are going to be some folks that are going to have the potential to look at how those two work together, for example, in the case of like smoking and things like that. So we want to be real solid about this sort of thing. If you have any questions, send me an email, send me a remind message, ask me in class. Otherwise, hope to see you again soon.